Silicon, the heart of our microchips, starts its journey in an unexpected place. Sand. Not just any sand, but quartz sand, rich in silicon dioxide. This abundant material holds the key to our digital world. The silicon dioxide in sand is chemically processed to extract pure silicon. This process is energy-intensive, but the result is remarkable. A silvery, metallic-looking material known as electronic-grade silicon. This highly purified silicon forms the foundation for the intricate world of microchips. The purified silicon is melted down in a high-temperature furnace. A single silicon crystal, called a seed crystal, is dipped into the molten silicon and slowly pulled upward. As the seed crystal is drawn up, the molten silicon atoms adhere to it, aligning themselves perfectly to create a large, cylindrical single crystal known as an ingot. This process, called the Czochralski process, is crucial for creating the perfect crystal structure needed for microchip functionality. These ingots, weighing hundreds of pounds, are breathtaking testaments to human ingenuity. The silicon ingot, a gleaming cylinder of pure crystal, is carefully sliced into thin discs using diamond saws. These discs, called wafers, are incredibly thin, often less than a millimeter thick. Each wafer is then polished to a mirror-like finish, removing any imperfections on its surface. These polished silicon wafers serve as the canvases upon which the intricate circuits of a microchip will be drawn. The precision required in this process is astounding. Even a tiny flaw can render a wafer useless. Photolithography. Painting with light. Now comes the magic of microchip fabrication, printing billions of transistors onto a surface smaller than a fingernail. This intricate process is the backbone of modern electronics, enabling the creation of powerful and compact devices. This process, called photolithography, utilizes light to etch patterns onto the silicon wafer. It's a precise and delicate method that requires a clean room environment to prevent any contamination. The wafer is coated with a light-sensitive material called photoresist. This coating is crucial as it reacts to light, allowing the intricate patterns to be transferred onto the wafer. A mask, containing the intricate circuit pattern, is placed over the wafer. This mask acts like a stencil, guiding the light to create the desired design. Ultraviolet light is shown through the mask, hardening the exposed photoresist while leaving the unexposed areas soft. This step is critical for defining the circuit pathways. The soft photoresist is then chemically removed, leaving the desired circuit pattern etched into the wafer. This final step reveals the intricate network of circuits that will power our electronic devices. Doping and etching. Creating the circuits. This is a crucial step in the semiconductor manufacturing process, where precision and expertise are paramount. The etched wafer undergoes a process called doping, where impurities are intentionally introduced into the silicon to change its electrical properties. This step is essential for defining the behavior of the silicon in electronic devices. These impurities, called dopants, create regions within the silicon that can conduct or resist the flow of electricity, forming the transistors, the building blocks of microchips. Without this precise doping, modern electronics wouldn't function as we know them. Etching, using a controlled chemical or plasma process, further refines the features on the wafer, creating the intricate network of connections between transistors. This step ensures that the microchip can perform complex tasks efficiently. The precision required is mind-boggling. The smallest features on a modern microchip are measured in nanometers, billionths of a meter. This level of detail is what allows for the incredible performance and miniaturization of today's electronic devices. Layering up. Building the microchip city. The process of photolithography, doping, and etching is repeated multiple times, layer upon layer, to create the intricate designs required for modern electronics. Each layer adds a new level of complexity to the chip, interconnecting transistors to form logic gates, memory cells, and other essential components. These layers must be precisely aligned to ensure proper functionality. The result is a three-dimensional structure of incredible density and complexity, capable of performing billions of calculations per second. This layering process is akin to building a microscopic city, where each layer is meticulously crafted to serve a specific purpose, with each layer representing a different level of infrastructure, power grids, communication lines, and pathways for data transfer, and functional units all intricately woven together. This complex network allows the microchip to perform its designated tasks efficiently and reliably. Testing, packaging, and the end of the journey. After the final layer is complete, the wafer undergoes rigorous testing, Each individual chip on the wafer is tested for functionality and performance. The chips that pass this rigorous quality control are then separated, encapsulated in protective packages, and prepared for shipment to computer manufacturers and other electronics companies. From the beaches to the factory floor, the journey of the microchip is a testament to human ingenuity and our relentless pursuit of technological advancement. If you like this video, don't forget to hit the like button and subscribe for more exciting content, updates, and new uploads from Manufactour straight to your feed.